Okay, so let's do one more. In this particular instance, we're going to do something just slightly bit different than what we've been doing in the previous few. I'm going to show you how we can solve this particular problem, and we're not going to use EI, UI, EG, or UG. I'm only going to use my rules of replacement, rules of implication, and CQ to solve this problem. So let's look at our premises and our conclusion. Premise 1 says for all x, if x is A, then there exists an x that's not B. Premise 2 says it's not the case for all x. If x is B, then there exists an x that's not C. And the conclusion says for all x, if x is C, then there exists an x that's not A. Okay? So one of the things I want to look at real quick is let's look at the consequent of line 1 and the antecedent of line 2. The consequent in line 1 says there exists an x such that x is not B. The antecedent of line 2 says it's not the case that for all x, x is B. So what line 2 is telling me is that, hey, there's at least one x in the world that's not B, because it's not the case that for all x in the universe that x is or B, okay? That's exactly what my consequent says right here. It says there exists an x such that x is not B. So my consequent in line 1 is equivalent to the antecedent in line 2. Which means, of course, we can use our quantifier exchange rule here. Now, if it wasn't already clear, we can use quantifier exchange on just part of my line here. Notice on both 1 and 2, my main operator is the horseshoe, okay? So these are conditional statements, which means I can use my rules of replacement on these. But right now, I can't seem to figure out what sort of rule of replacement or implication I can use. And I misspoke just a minute ago. You can always use your rules of replacement on these things, but in this case, since my main operator is the horseshoe, I can also use my rules of implication. The thing is, I can't seem to figure out what rule of implication I want to use, but now that I notice that my consequent in line 1 is equivalent to my antecedent in line 2, if I do quantifier exchange, then it looks like it'll give me a hypothetical syllogism. So let's do quantifier exchange on line 2, and I'll show you. So on line 3, we'll write there exists an x such that x is not B implies that there exists an x such that it is not C, and this will be from 2 CQ. Now notice I didn't do anything to the consequent on line 2. I just did quantifier exchange on the antecedent of line 2 so that it would match up with my consequent on line 1. Now we can use a familiar rule, which is hypothetical syllogism. Line 1 says if for all x, x is A, then there exists an x that's not B. Line 3 says there exists an x that's not B implies that there exists an x that's not C. So if it's the case that for all x, x is A, then there exists an x that's not B, and it's the case that if there exists an x that's not B, then there exists an x that's not C, that means that if it's the case that for all x, x is A, then it's the case that there exists an x that's not C. So we can write that down via hypothetical syllogism. That'll be from 1, 3, HS. So just to make sure it's clear, let's talk about hypothetical syllogism again for a second. Remember how hypothetical syllogism works. If I have a P, then I have a Q. If I have a Q, then I have an X. That lets me know that if I have a P, then I have an X. Okay? And the reason for this is that what I'm telling you is that every single time I have a P, I'm going to have a Q. And every single time I'm going to have a Q, I'm going to have an X. Which of course then means every single time I have a P, I'm going to have an X. All right? So this is our hypothetical syllogism rule. Notice I do the same thing right here. Right? Line 1 says every time that I have for all x, x is A, then I'm going to have that there exists an x that's not B. And line 3 says, and every time I have an x that exists that's not B, then I'm going to have an x that exists that's not C. Okay? Therefore, I know that if I have for all x, x is A, then I'm going to have there exists an x such that x is not C. So notice what I show you right here is the exact same thing that I'm doing with 1 and 3 to get line 4. Okay? All right. So let me erase this, and then we can finish the problem up. So at line 5, I'm going to use a rule that you may not use very often, but it comes in pretty handy, and that's transposition. Because again, I'm trying to get to this conclusion right here, which tells me that for all x, if x is c, then there exists an x that is not a. But the way this is stated is kind of backwards of that. Notice my antecedent here says that for all x, x is a, then there exists an x such that x is not c. So if I do transposition, which means I can turn this around, but it puts a negation in front, so transposition allows me to write this down. It is not the case that there exists an x that is not c, implies that it is not the case for all x, ax. All right, and this is from 4 transposition. Now let's talk about transposition for a second here. So transposition looks like this. If I have a P, then I have a Q is equivalent to if I don't have a Q, then I don't have a P. Now we know we can prove this through our other rule, modus tollens. So think about it. Right here it says if I have a P, then I have a Q. What's it mean if I don't have a Q? Well, if I don't have a Q, then that would mean I don't have a P. Okay? So basically, if P implies Q, then that means not Q implies not P. That's exactly what my rule of transposition tells me. And so that's the move I make from 4 to 5. I just simply perform transposition on 4, which allows me to get the line that I have at line 5. Okay. So now that I have my statement on line 5, I can then finish up my proof here. Because look, my conclusion says for all x, if x is c, then there exists an x such that that x is not a. All right? Now, if it's the case that for all x, x is c, what am I actually saying? I'm telling you that it's not the case that there exists one single x that's not a c. Well, what does that say? That says it's not the case that there exists a single x that's not c. So in other words, for all x, x is c. So my quantifier exchange rule allows me to do that, and it's going to allow me to do the same thing to my consequent. Look at what that says. It says there exists an x such that x is not a. Well, that's exactly what this says. It's not the case that for all x, x is a. In other words, it's not the case that for every single x in the universe that that x is a freaking a, okay? It's possible that there's at least one x out there that's not a, and that's what my conclusion says. So since this and my conclusion are equivalent and mean the same thing, I can use quantifier exchange rule right here on this consequent to change it to that. So I end up with there exists an x such that x is not a, right? Which just tells me that it's not the case that for every x in the universe it's got to be an a. Okay, so now what I can do is just notate that. That's 5CQ, and I've solved the problem. Now notice I didn't use any of my instantiation rules or my generalization rules here. My main operators all the way through, right here, 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 were all conditionals. So since I have main operators as conditionals, I'm free to use my rules of implication like hypothetical syllogism. The big move here was just using CQ a couple times to turn things around to get them into a position so that I could use my rules of implication. And then on that last line, using CQ just to change my quantifiers around so that they fit with my conclusion, okay? So I hope that you guys are starting to get this, and I hope that the videos are helping out a lot. Good luck, and keep working hard.